Every single engineer at the Naval Research Laboratory delivered the same verdict. The concept was fundamentally flawed. Building a radio transmitter compact enough to fit within an artillery projectile, durable enough to withstand the tremendous shock of cannon fire, and precise enough to sense an enemy plane and detonate at the perfect instant simply violated the known laws of physics. The acceleration forces alone would obliterate any electronic device that existed in the late 1930s. The engineers who delivered these verdicts were not pessimists or obstructionists. They were highly trained professionals, many with advanced degrees from prestigious universities like MIT, Caltech, and Columbia, who had spent years working with the electronic equipment and understood its limitations intimately. They had designed radar systems for detecting ships and aircraft, radio communication equipment that operated across thousands of miles, and various electronic instruments for military applications ranging from submarine detection to fire control systems. They knew what components could and could not withstand. They had conducted countless tests in laboratories and field conditions, analyzed numerous failures where components broke or circuits malfunctioned, and developed a deep understanding of where the boundaries of possibility lay through years of practical experience and theoretical study. When they said something was impossible, they spoke from experience and knowledge, not from ignorance or timidity. These were men who had pushed the boundaries of electronics in multiple fields. Some had worked on early television systems, wrestling with the challenges of transmitting moving images across distances. Others had developed sophisticated instruments for measuring radio wave propagation or for detecting submarines through electromagnetic means. They had seen what worked and what didn't. They understood the difference between laboratory curiosities and practical devices that could function reliably in the real world. Their skepticism was rooted in hard engineering reality, supported by mathematics and experimental data. They could point to specific, quantifiable reasons why the proximity fuse wouldn't work. The vacuum tubes would shatter under acceleration, their glass envelopes exploding into powder, or their internal elements breaking loose and rattling around inside the tube. The circuits would short out when solder joints failed or when wires broke free from their terminations, creating random connections that would either prevent operation entirely or cause the device to trigger at the wrong moment. The power supply would fail when the battery's internal plates deformed, or when the electrolyte leaked, or when connections between cells broke under stress. The antenna would break off during firing, snapped away by aerodynamic forces as the shell left the gun barrel at supersonic speeds, leaving the fuse unable to transmit or receive signals. The detonation mechanism would trigger prematurely, either from false signals generated by electrical noise or from mechanical shock jarring the firing circuit, causing shells to explode inside gun barrels or immediately after firing, or it would fail to trigger at all when the detection circuit was damaged or when the detonator was rendered inoperative by the violence of launch. Each component presented insurmountable challenges, and fixing one problem invariably created others or revealed additional difficulties that hadn't been apparent initially. Even if you solved one problem, a dozen others remained. The engineers had seen similar ambitious projects fail before. They had witnessed the gap between laboratory demonstrations, where equipment sat safely on benches in controlled environments, and field-ready weapons that had to function after being dropped, shaken, frozen, heated, and subjected to all manner of abuse. They understood how difficult it was to make any electronic device reliable under benign conditions, let alone under the violence of artillery fire. A home radio that worked perfectly in a living room, how completely if you simply moved it to a different location or operated it in a damp basement. Military equipment had to be vastly more reliable, and even then, failure rates were often discouragingly high. Molotov held a different opinion about impossibility. Throughout his career, he had developed a reputation for approaching problems that others dismissed as unsolvable. His background in physics and his experience with emerging radar technology had taught him that the boundaries of possibility were often more flexible than conventional wisdom suggested. He had seen too many supposedly impossible things become routine to accept pronouncements of impossibility without question. Born in Canton, South Dakota in 1901, Tuve had grown up in the American Midwest during a time of rapid technological change. His father, Anthony Tuve, was a Norwegian immigrant who had settled in the small prairie town and established himself as a schoolteacher and administrator. The elder Tuve valued education intensely, having seen firsthand how knowledge and learning created opportunities that physical labor alone could never provide. He created an intellectually stimulating environment for his children, expecting them not merely to attend school, but to genuinely learn, to question, to understand. The family home contained books on science, history, and literature, shelves lined with volumes that were read and discussed rather than merely displayed for show. Discussions at the dinner table ranged across mathematics, where the elder Tuve would pose problems for his children to solve, natural philosophy, examining questions about the physical world and how it operated, and current events, from local politics to international developments. Young Merle absorbed this atmosphere of intellectual curiosity and developed a fascination with understanding how things worked. He would disassemble clocks and mechanical toys, studying their mechanisms, not content merely to use them, but needing to comprehend their operation. He built crystal radio sets, winding coils of wire around oatmeal boxes and searching for the faint signals of distant stations. He conducted chemistry experiments in the family shed, sometimes to the alarm of his parents when reactions produced unexpected results. Canton itself was a town of perhaps 2,000 souls, situated on the windswept Dakota plains where the horizon stretched endlessly in all directions. The landscape was flat agricultural country, broken only by occasional rises, and the trees planted as windbreaks around farmsteads. In winter, bitter cold descended from Canada, dropping temperatures to 20 or 30 degrees below zero, sometimes lower. Cold that could freeze exposed flesh in minutes, and that made any outdoor activity painful and potentially dangerous. In summer, the heat could be oppressive, with temperatures climbing into the 90s and the sun beating down from cloudless skies, baking the earth and withering crops if rain failed to come at the right times. It was a place that bred either resignation or determination, where people either accepted their circumstances as unchangeable or resolved to change them through force of will. Tuve chose determination. He had witnessed the transformation from horse-drawn carriages to automobiles rumbling down Main Street, raising clouds of dust in summer and struggling through snowdrifts in winter. The first automobiles in Canton were objects of wonder and skepticism. Farmers questioned whether these mechanical contraptions would ever be as reliable as a good team of horses. When the automobiles broke down, as they frequently did on the primitive roads, critics felt vindicated. But the automobiles kept improving. They became more reliable, more powerful, more practical. Within a few years, they were commonplace, and the skeptics had become converts or had been proven wrong by events. He had seen gas lamps replaced by electric lighting, watching as the town installed power lines and as homes switched from the soft yellow glow of gas to the bright white light of incandescent bulbs. Electric power came to Canton in stages, first reaching businesses on Main Street, then expanding to residential areas, transforming daily life in ways both obvious and subtle. Work could continue after dark without the dimness and smell of gas lamps. Reading became easier. Businesses could remain open later. The change seemed miraculous to those who remembered the old ways, yet within a short time it became simply normal, expected, unremarkable. He had watched telegraph give way to radio, communication transformed from coded messages, tapped out one letter at a time to voices, and music transmitted through the air across vast distances. The first time young Merle heard a radio broadcast, picking up a distant station on his homemade crystal set, it seemed like magic. A voice speaking from hundreds of miles away, transmitted through invisible waves, received by a simple device he had built himself from wire, crystals, and scavenged parts. The technology was new enough that not everyone understood it or believed it. Some people thought radio receivers must be connected by hidden wires. Others suspected fraud or trickery. But Tuve understood the physics, had read about electromagnetic waves and how they propagated through space. He knew it was real, and he knew it was just the beginning. This experience had instilled in him a belief that technological barriers were temporary obstacles rather than permanent limitations. What seemed impossible today might be routine tomorrow. The question wasn't whether something could be done, but rather when it would be done and who would do it. Skeptics always existed, people who would explain in great detail why something wouldn't work. Sometimes they were right. Often they were proven wrong by someone willing to try anyway. Tuve had excelled academically, showing particular aptitude in mathematics and the physical sciences. He left Canton to attend the University of Minnesota, where he studied physics under professors who recognized his exceptional talent. Minnesota had a strong physics department, with faculty conducting research in various areas, including ionospheric studies and cosmic rays. Tuve immersed himself in experimental work, spending long hours in laboratories, learning to use equipment, to design experiments, to interpret data. He learned that physics wasn't merely about understanding theories, but about testing them, about building apparatus that could reveal nature's secrets. He earned his bachelor's degree in 1922, distinguishing himself enough to be accepted into the doctoral program at Johns Hopkins University, one of the premier research institutions in the country. At Hopkins, he worked under the supervision of distinguished physicists who were pushing the boundaries of knowledge in multiple fields. His doctoral research focused on measuring the wavelength of X-rays with unprecedented precision, work that required designing and building sophisticated apparatus and conducting measurements with extreme care. The work taught him that precision was achievable if you were willing to be meticulous enough, patient enough, clever enough in designing experiments, and eliminating sources of error. After completing his doctorate in 1926, Tuve joined the Department of Terrestrial Magnetism at the Carnegie Institution of Washington, a research organization dedicated to advancing scientific knowledge. The Carnegie Institution provided an ideal environment for someone with Tuve's interests and abilities. It had excellent facilities, adequate funding for research, and a culture that valued both theoretical understanding and practical application. Researchers were given considerable freedom to pursue their interests, constrained more by their imagination and ability than by administrative requirements or narrow program goals. At Carnegie, Tuve became involved in pioneering radar research, though it wasn't called radar yet. The term wouldn't be coined until later. In the early 1930s, it was radio echo work or pulse radio detection. Experiments designed to measure the height of the ionosphere by sending radio pulses upward and measuring the time delay before receiving reflections. The ionosphere was a layer of ionized gas high in Earth's atmosphere that affected radio wave propagation, particularly at night when long-distance radio communication became possible through reflections off this layer. Understanding the ionosphere's height and properties was important for both scientific knowledge and practical applications in radio communication. The experiments required generating powerful radio pulses, transmitting them upward with directional antennas, and detecting the extremely weak reflections that came back. The reflected signals were often millions of times weaker than the transmitted pulses, requiring extraordinarily sensitive receivers and careful technique to detect them amid noise from natural sources and man-made interference. Tuve and his colleagues built high-power transmitters capable of generating kilowatts of radio frequency energy in short bursts. They designed receivers with enough sensitivity to detect signals only millionths of a volt in strength. They developed techniques for displaying the received signals on oscilloscopes so they could measure the time delays with precision. This work put him at the forefront of understanding radio wave reflection and detection, experience that would prove crucial When the proximity fuse project began, he understood how radio waves propagated through space, how they reflected from objects, how their strength diminished with distance according to well-established mathematical relationships. He knew how to design transmitters and receivers, how to match impedances for maximum power transfer, how to minimize noise in sensitive circuits. He had practical experience building equipment that worked, not just in laboratories, but in field conditions where weather and terrain posed challenges. He had learned to solve problems through a combination of theoretical understanding and practical experimentation, trying different approaches when initial attempts failed, refining designs through iteration. By 1940, Tuve had established himself as one of America's leading experimental physicists, with a particular expertise in radio technology and ionospheric research. He had published numerous papers in prestigious journals. He had given presentations at scientific conferences, sharing his findings with colleagues. He had trained graduate students and younger researchers, passing on his knowledge and approach to problem solving. He had a reputation for tackling difficult problems and finding solutions through a combination of theoretical insight and experimental skill. When the proximity fuse project needed a leader, someone who understood both the physics and the engineering, someone who wouldn't be deterred by declarations of impossibility, Tuve was an obvious choice. On a frigid November morning in 1940, with war spreading across Europe and the United States preparing for likely involvement, he stood in his laboratory at the Carnegie Institution in the nation's capital. Outside, the temperature hovered just above freezing. A thin layer of frost covered the windows. The sky was overcast, heavy grey clouds promising rain or perhaps snow if the temperature dropped further. Washington in November could be bleak, the trees bare of leaves, the grass brown and dormant, the shortened days offering little sunlight even at midday. The room smelled of solder and electrical components, familiar scents that any electronics laboratory would have. Solder, an alloy of tin and lead, had a distinctive odor when melted by a hot soldering iron. Electrical components, particularly resistors and transformers, emitted subtle smells, especially when new or when warm from operation. The workbenches were cluttered with oscilloscopes displaying glowing green traces on their screens, power supplies with their heavy transformers and voltage adjustment knobs, and fragments of experimental devices representing iterations of design and testing. Oscilloscopes were essential tools for anyone working with electronics, allowing you to visualize voltage waveforms and measure timing with precision. The power supplies provided the various voltages needed to operate circuits, adjustable to whatever values a particular experiment required. The walls were lined with shelves holding vacuum tubes of different types, small signal tubes for amplification, power tubes for generating higher voltages and currents, special purpose tubes for specific applications. There were resistors, small cylindrical components with colored bands indicating their resistance values, ranging from a few ohms to millions of ohms. Capacitors of various types filled other shelves. Ceramic disc capacitors the size of a button, paper capacitors rolled into cylindrical packages, electrolytic capacitors with their distinctive aluminum cases and wire leads. There were coils of wire in different gauges, spools of solder, boxes of screws and hardware, tools of every description from screwdrivers and pliers to specialized equipment for working with small components. Schematic diagrams covered the walls. Sheets of paper showing circuit designs with standard electrical symbols for resistors, capacitors, tubes, and other components. The diagrams were marked with notations and corrections in multiple colors of ink, red showing changes from original designs, blue indicating values that had been tested, black for initial concepts, each color representing a stage, the development process. Some diagrams had calculations scribbled in margins, equations relating to frequency response or gain or power consumption. Others had notes about component failures or ideas for improvements. The accumulation of marks and notes told a story of intensive development work, of ideas tried and rejected, of problems identified and solved. The laboratory had the organized chaos characteristic of intense research activity, where every surface held something important and every drawer contained critical components. To an outsider, it might appear cluttered or disorganized, but Tuve knew where everything was. He could locate a specific component or tool without searching. The arrangement represented a working system, optimized not for appearances, but for efficiency in conducting research and building experimental apparatus. There was a logic to the layout, with related items grouped together, frequently used tools within easy reach, less common items stored, but accessible when needed. In his hands rested a prototype triggering mechanism weighing under 2 pounds. After picking it up from the workbench, where it had been undergoing final tests, he turned it slowly, examining it from different angles, feeling its weight and balance. 2 pounds seemed impossibly light for a device that would revolutionize warfare. A bag of sugar weighed more, yet this small assembly of electronics and mechanics represented months of intensive work by talented engineers and scientists, thousands of hours of effort, countless experiments and failures and refinements. The device was cylindrical, roughly 3 inches in diameter and 4 inches long, small enough to fit in the palm of his hand. Its dimensions had been determined by the space available in a 5-inch shell's nose, with allowances for mounting and for the explosive behind it. Every fraction of an inch mattered. Make it larger and it wouldn't fit. Make it smaller and you couldn't pack in all the necessary components. The size represented a compromise between what was needed and what space was available. A compromise arrived at through careful analysis and numerous design iterations. The exterior was made of machined aluminum, chosen for its light weight and adequate strength. Aluminum was 1/3 the weight of steel for the same volume, critically important when every ounce had to be justified. The aluminum had been machined on precision lathes, cut to exact dimensions, with tolerances measured in thousandths of an inch. The surface was smooth, with threading at one end for installation in the shell and mounting points for attaching internal components. Machining aluminum required skill, because the metal was soft and could be damaged by improper tooling or technique. The machinists who produced these housings were craftsmen, trained to work to exacting standards. Within this small device sat 4 tiny vacuum tubes, each one representing months of failed experiments and incremental improvements. These tubes were unlike anything in commercial production. They were smaller than conventional tubes, measuring perhaps half an inch in diameter and an inch in length. Miniaturization was essential, but small size created additional challenges. Smaller tubes had less surface area for dissipating heat. Their internal elements had to be positioned with even greater precision because any deviation affected performance more severely. In a compact design, they had been designed from first principles to survive conditions no electronic component had ever faced. The glass envelopes were made from special high-strength glass, thicker than standard tube glass, but still thin enough to seal properly during manufacturing. The composition of the glass had been adjusted to give it greater resistance to shock and thermal stress. The internal elements, the cathode, grid, and plate, were smaller and more robust than in conventional tubes. The cathode was secured rigidly rather than suspended on thin wires. The grid was made from heavier wire than usual, sacrificing some electrical performance for mechanical strength. The plate was designed to withstand deformation without touching other elements. The tubes were potted in a special compound, surrounded by material that would absorb and distribute shock forces. The potting compound was a mixture of wax and other materials that remained somewhat flexible even after hardening. When the tube experienced acceleration, the potting compound would compress, cushioning the tube and preventing the internal elements from moving relative to the glass envelope. Developing the right potting compound had required extensive experimentation. To soft, and it wouldn't provide enough support. To hard, and it would crack under stress, potentially damaging the tubes rather than protecting them. The filaments that heated the cathodes to emit electrons were coiled from special wire, heavier gauge than standard filament wire and wound under tension so they wouldn't sag or break under acceleration. The filaments were designed to operate at lower temperatures than conventional tubes, extending their life at the cost of some efficiency. Lower operating temperature meant the cathode coating wouldn't deteriorate as quickly and the thermal stress on the tube would be reduced. The trade-off was acceptable because the tubes only needed to function for a few seconds from launch to detonation, a power supply designed to function after experiencing forces 20,000 times normal gravity occupied another section of the mechanism. The battery was a remarkable achievement in itself, representing as much innovation as the tubes or the radio circuit. Standard batteries of the era would be destroyed instantly by the acceleration of gun firing. The liquid electrolyte in conventional batteries would slosh violently, potentially causing short circuits or breaking internal connections. The plates would bend or break free from their supports. The casing might rupture, spilling caustic chemicals that would damage other components. This battery was entirely different in construction. It consisted of multiple cells connected in series to provide the necessary voltage, typically around 90 volts for the plate supply and separate lower voltages for the filaments. Each cell had been specially constructed with thick paste electrolyte that wouldn't slosh or deform under acceleration. The paste was formulated to have the right consistency, thick enough to stay in place, but not so thick that it impeded the chemical reactions that generated electrical current. The formulation had been developed through extensive testing, trying different compositions and measuring their performance under simulated firing conditions. The internal plates were made from lead and lead dioxide, the standard materials for battery construction, but they were reinforced and secured to prevent movement. Each plate was held rigidly in place by multiple supports, rather than the single mounting point used in conventional batteries. The plates were thicker than normal, better able to withstand stress without bending. The spacing between plates was carefully controlled because variation would affect the battery's electrical characteristics. The entire battery assembly was potted in a shock-absorbing compound that helped distribute forces evenly. Like the potting for the tubes, this compound had to have specific properties. It needed to be electrically insulating to prevent short circuits between cells. It needed to remain somewhat flexible to absorb shock. It needed to not degrade over time or under temperature variations. It needed to not react chemically with the battery materials. Finding a compound that met all these requirements had been challenging. The battery had to provide stable voltage throughout its operating life, which admittedly was short, only the few seconds from launch to detonation. But during those seconds, it had to supply current reliably, despite having been subjected to enormous violence during firing. Tests had shown that the battery maintained adequate voltage even after being subjected to accelerations far exceeding what it would experience in normal operation. The design incorporated safety margins, built to withstand forces beyond the expected maximum. The radio circuit, so miniaturized it resembled something from speculative fiction, filled the remaining space. In 1940, the idea of packing a complete radio transmitter and receiver into a space smaller than a cigar box seemed absurd. Home radios filled cabinets. Military radios required cases the size of suitcases. Yet here was a complete radar system in a fraction of that volume. The miniaturization had been achieved through careful design, ruthless elimination of anything non-essential, and clever arrangement of components. The circuit included a transmitter that generated radio frequency pulses at approximately 200 MHz in the VHF portion of the spectrum. 200 MHz provided a good compromise between various competing requirements. Lower frequencies would require larger antennas for efficient transmission and reception. Higher frequencies would provide better resolution, but would require components that were more difficult to manufacture and less forgiving of imperfections. The transmitter used one of the vacuum tubes as an oscillator, generating the carrier frequency, and another tube to pulse the oscillator on and off, creating the brief bursts of radio energy that would propagate outward from the shell. A receiver detected reflections from nearby aircraft. The receiver used the remaining tubes to amplify the extremely weak signals that bounced back from metal aircraft structures. The sensitivity of the receiver was crucial. The reflected signals might be billions of times weaker than the transmitted pulses, reduced by the tremendous attenuation that occurred when radio waves traveled to the target and back. The receiver had to amplify these weak signals enough to be detectable, while not amplifying noise so much that the system would trigger falsely. An amplifier boosted the weak, reflected signals to a level that could trigger the detonator. The amplifier was designed to respond to signals at the right frequency and to ignore signals at other frequencies, providing some discrimination against interference. The output of the amplifier went to a detection circuit that would close a switch when the signal exceeded a threshold, initiating the detonation sequence. Every component had been carefully selected and tested. Nothing was included that wasn't absolutely necessary. Every component served a specific purpose, and alternative approaches had been evaluated before settling on the final design. The selection process had involved extensive testing of candidate components under simulated firing conditions to ensure they could survive. The resistors were wire wound types that could withstand shock. Standard carbon composition resistors, made by mixing carbon powder with a binder and forming it into a cylinder, were too fragile. They would crack or shatter under high acceleration, while wound resistors, made by winding resistance wire around a ceramic core, were much more robust. They cost more and were larger for a given resistance value, but they could survive conditions that would destroy carbon resistors. The capacitors were ceramic rather than the larger paper capacitors used in conventional radios. Paper capacitors consisted of sheets of metal foil separated by paper impregnated with wax or oil, rolled into a cylinder, and enclosed in a metal case. They worked well under normal conditions, but were too fragile for the proximity fuse application. Ceramic capacitors were made by coating both sides of a ceramic disc with silver and attaching wire leads. They were much smaller than paper capacitors and could withstand extreme conditions, though they had limitations in capacitance values and temperature stability. Every connection was soldered with special high-strength alloy and then mechanically reinforced. The solder used a formulation with higher mechanical strength than standard electrical solder, achieved by adjusting the tin to lead ratio and adding small amounts of other metals. Each solder joint was made carefully, with the iron held at the right temperature and the joint allowed to cool slowly to avoid creating stresses in the solidified solder. After soldering, critical connections were mechanically reinforced by wrapping wire around components or by using small clamps to ensure that even if the solder cracked, the electrical connection would be maintained. The wiring itself was special, with insulation that wouldn't crack under stress and conductors that were stranded rather than solid. Stranded wire consisted of multiple small diameter wires twisted together, more flexible and less prone to breaking from vibration or bending than solid wire. The insulation was a rubber compound formulated to remain flexible over a wide temperature range and to resist degradation from heat, ozone, and the various chemicals it might encounter. Within half a year, this mechanism would be installed in a 5-inch naval shell and launched at an unmanned target aircraft above the Chesapeake Bay. A test that would validate or invalidate months of work. The test would be conducted under realistic conditions, not the idealized environment of a laboratory. The shell would be fired from an actual 5-inch gun aboard a Navy vessel. The target would be a drone aircraft flying at realistic altitude and speed. Observers would watch and document the results with cameras and through visual observation. Success would revolutionize combat at sea, providing a solution to the air defense problem that had plagued navies since aircraft had become effective anti-ship weapons. Failure would mean years of intensive engineering effort wasted by hundreds of skilled workers, not to mention the millions of dollars in research funding that would be difficult to justify to military leadership already skeptical of the project. The Navy had invested heavily in this program, diverting resources from other projects that had more certain outcomes. Money that might have gone to building more ships or developing other weapons had been allocated to proximity fuse research. The decision had required courage from the officers who championed the program, who believed the potential payoff justified the risk. Officers who had championed the proximity fuse had staked their careers on its success. If the project succeeded, they would be recognized as visionaries who had supported crucial technology. If it failed, they would be seen as men who had wasted resources on an impractical dream, while the nation was preparing for war. Their professional reputations hung in the balance alongside the technical success of the device Tuve held in his hands. The challenge of anti-aircraft gunnery was straightforward to articulate, but appeared utterly beyond solution to anyone who examined it carefully. Shooting down aircraft in 1940 involved mathematics, trajectory prediction, and remarkable fortune. The problem combined elements that were individually difficult and collectively seemed impossible. You had to detect the target, determine its course and speed, predict its future position, aim your weapons, fire at the right instant, and hope that your shell would explode at the right place and time. Each step introduced uncertainty and potential error, and the uncertainties compounded. A bomber traveling at 15,000 feet altitude and 200 miles per hour represented a target moving through three-dimensional space. To visualize the problem, imagine a dot in the sky, a small speck visible against clouds or blue sky, moving steadily in some direction. That's the target. It's not stationary. It's not moving in a simple straight line at ground level, where you can easily judge distance and speed. It's up in the air where perspective is difficult, where judging distance requires instruments or great experience, where the slightest change in heading produces a significant change in position after a few seconds. The pilot might alter course at any moment, turning left or right, climbing or descending. Pilots under attack wouldn't maintain steady flight. They would maneuver, trying to evade defensive fire by changing their flight path unpredictably. A pilot might wait until he saw gun flashes from below, then immediately begin evasive action, turning hard and changing altitude. The defensive fire aimed at where the aircraft had been would miss because the aircraft was no longer there. This made prediction extraordinarily difficult. You couldn't just calculate where the aircraft would be based on its current motion. You had to anticipate evasive maneuvers, which was essentially guessing. Wind conditions changed constantly, affecting both the aircraft's movement and the shell's trajectory. Wind aloft was different from wind at ground level, both in speed and direction. Jet streams weren't understood in 1940, but pilots and navigators knew that wind patterns at altitude could be complex. A strong wind from one direction could push an aircraft off course by miles, if not corrected. The same wind would push a shell traveling through it, deflecting its path from the calculated trajectory. Wind speed and direction often varied with altitude, so a shell fired upward would experience different winds at different points in its flight, each one affecting its path. The aircraft's altitude fluctuated as pilots maneuvered to evade defensive fire, diving toward the deck or climbing to escape the reach of guns. An aircraft at 15,000 feet might suddenly nose down and descend to 10,000 feet in less than a minute, completely invalidating the firing solution calculated for 15,000 feet. Or the pilot might advance throttles and climb, gaining altitude to get above the effective range of the guns. These altitude changes complicated prediction enormously because they occurred in the third dimension, harder to detect and measure than changes in horizontal position. The intercepting shell traveled at 2,000 feet each second, an enormous velocity that compressed the time available for interception, but also meant that small errors in prediction became large errors in position. At 2,000 feet per second, the shell covered nearly 1,400 miles per hour, faster than any aircraft of the era by a factor of 5 or more. This speed meant that calculations had to be extraordinarily precise because a timing error of even a tenth of a second would result in a position error of 200 feet. Gunners had to aim where the plane would arrive, not its current position. This is the fundamental challenge of hitting a moving target with a projectile that has travel time. You can't aim at where the target is now because by the time your projectile arrives, the target has moved. You must aim at where the target will be when the projectile gets there. For slow-moving targets at short ranges, the lead required is small enough that experience and instinct can suffice. For fast-moving targets at long ranges, the lead becomes so large that calculation is essential and even small errors cause complete misses. Think about the complexity of this calculation in detail, breaking down all the factors that had to be considered. The shell took perhaps 15 or 20 seconds to reach the target's altitude, depending on the range and angle of fire. Those 15 to 20 seconds represented an enormous interval when you were trying to predict the position of a moving aircraft. During those seconds, a bomber traveling at 200 miles per hour would move more than half a mile horizontally, over 2,600 feet, a distance comparable to the length of several city blocks. The gunners had to predict not just where the aircraft would be in 15 seconds, which by itself would be challenging, but also account for multiple additional factors,